Good morning, everyone. We're just going to wait a little bit as people join. Okay, so we're going to slowly start. So this is Phoebe closing webinar. Thank you all for joining us. We come to an end of a 3.5 years journey. So today is the time for us to share the outcomes of Phoebe. This webinar is being recorded, so just so you know, I'm just going to show what we have in the agenda for today. Just going through the work done in Phoebe, showing the framework, looking at the pilots and the results, and then more in detail in the different modules of our framework with multi-choice modeling, the integration into the framework, the behavior modeling as well, the IREP, VIDA, and AIMSAN integration, and then a little bit more in detail in the results. Don't be shy about asking things. You can put everything on the chat. We will make sure to try to reply to everything. As I mentioned, this is being recorded, so don't forget to reach out to us or check our website to see the recordings and all the other work that we have, all the deliverables, everything in more detail. And we are also happy to share everything that is needed on one-to-one. So I think people are slowly joining. So I will stop here and I will pass on to Shanna so she can give an overview of our project. And that's it.
Thank you very much, Andrea. Let me very quickly share my screen. I hope you can see my screen well. So hello, everyone. Thank you very much for joining this final event for the Phoebe project. I will start with a brief overview of the project and what we aim to achieve at the end and what we have achieved at the end. But my colleagues that are also present in this call will go do a deep dive into the more technical parts of the methodology that we developed and also on the use case. And then I'm back to show a little bit about the results. So my name is Shana Lucchesi. I work as the Road Safety Innovation Manager for the European Institute of Road Assessment, and here I'm representing ERA and IREP. So a little bit about the project itself. So the project is funded by the European Union and the UK Research and Innovation. We are a research and innovation project. So this means that we are very interested in the journey, not only in the final destination. So we want to learn and develop innovative ways of doing proactive road safety assessment in this project. We are 11 partners, as you can see in the map, from different backgrounds, from academia, from industry, but also some from the third sector, so charity as IREP and ERA. Basically the need, so why we starting this project at first place? So we understand that cities are very dynamic and complex environments, and it's very difficult for cities to really understand the whole impact of the interventions they are planning for their urban environments. Due to this complexity of the urban traffic systems, simply simulations or simply road assessments are not really showing the whole picture. So what we aim here is putting everything together to provide a very holistic way of assessing the impact of the interventions. We are quite aware that when cities are trying to simulate, for example, these changes, most of the results that they are getting from the simulations are very focused on vehicular traffic. And what we aim here at Phoebe as well is putting a little more weight on the vulnerable road users. So giving a little bit more of information on the impact for pedestrians, bicyclists, and motorcyclists as well. So we understand that there is this lack of integration of all of these tools. So basically what we are trying to provide here is a framework that connects and enhances simulations to, again, assess impact of interventions. But now we are very ambitious with this project. We are trying to go looking on not only the individual level, so how users are behaving for this intervention, but which is the impact of this network-wide, so in the macro level. And we want to that the framework will be able to assess the impact on new forms of transport, new technologies, or any regulatory and behavioral change. And again, with focus on vulnerable road users, not only vehicle occupants. We also aim that the PHOEBE framework will be a kind of like a blueprint. So we are not developing a tool properly, but it's basically a way to do these assessments. We are testing this methodology with several tools that you will see in a minute. But the idea is here that this could be replicable with different softwares, with different methodologies. What we are trying here is really create the path on how can we do these more holistic assessments. So the project objectives, very quickly, is to develop this new replicable methodology for dynamic safety prediction and socioeconomic evaluations. For this, we had to do some type of harmonization of safety definitions between risk assessments and traffic simulation models. We want to enhance and integrate urban risk assessment models and tools and embody the social components into risk assessment and traffic simulation, especially human behavior and mode and trip choice. As part of the project, we also look at exploit big data and telematics through AI and machine learned data analysis techniques that you will see some examples in these presentations, and apply all of this in real use cases. So we have experimental multi-use cases in 3 different locations that you're going to hear a little bit more as well. Our methodology is basically, and what the PHOEBE framework is trying to do, and what we also test in this project, is this 4-step methodology. So first we select the locations where we want to do simulations. Then we gather the data and enhance the simulation software with these additional components to run these evaluations and then extrapolate this network-wide. So the PHOEBE framework, in a nutshell, is trying to do this. It's getting the established and proven traffic simulation tools. In this project, we are using AIMSUM Next, but the idea is that, the framework will be software agnostic, and connect this with road safety assessment methods. In this project, we are using the IRAP star ratings, but again, could be a different methodology. Could be the European, for example, road safety assessment tools. But here we are then connecting the star ratings with the AIMSUM Next with a dedicated road safety model in traffic simulation tools. But again, not only that, bringing to this perspective also the human behavior component. So we are enhancing simulations with human behavior models that will do a more proper way of simulate behaviors inside of these tools. And also with the model shift and induced demand model. So basically how these interventions are also changing the way that people travel and how they are inducing new travels as well. And all of this, of course, with the idea of getting new and innovative data sources, especially using AI and machine learning techniques. So the project starts developing methodologically how the simulations can be enhanced. I know this can be quite complicated at first glance, but stay with me that I will just run you through quickly on the framework. So we start with step 1, that is basically setting the baseline scenario. So how is the people traveling, behaving? How is the risk in the actual states of the network? So basically we are combining here road safety assessment, demand models, behavior models into traffic simulations. We start with a very basic and preliminary risk assessment. But then the result of this risk assessment will be inputted into the demand models, because we understand that people will define how they travel based also on risk. So we are getting this information as a variable inside of the demand models. Parallel, we are looking for the behavioral components. So for example, in case of like speeding behavior, we are looking of what are the variables that are making people speed. So my colleagues will go into more details into the demand model and behavior model later on. And then we incorporate all of these into the traffic simulations. After running the traffic simulations, the output of the simulation, especially the speed and flows, will go back to road safety assessment to a more dynamic evaluation of risk in the baseline. And then we pretty much replicate the same thing for the step 2, that is the new scenarios, with some some necessary setups previously to give some insights to the demand models as well. But here in the step 2, we then incorporate the changes, even if it's like infrastructure changes, if it's regulation changes, new technologies, etc. We applicate that into the traffic simulation scenarios and also into the risk assessment scenarios to be able to rerun all of this in the step 2. And then with the results of step 1 and the results of step 2, there is a set of performance indicators that we are going to present as well later on. We'll be able to run some socioeconomic analysis that will look into details, into some set of parameters that will give us some cost-benefit analysis later on. So this is basically how the framework operates. Again, the whole objective is to enhance the simulation results, bringing into the simulation softwares, the risk assessment, the demand models, and the behavior models. So going quickly in a little bit more details on these 3 components that enhance the simulation. So we start with the demand modeling and socioeconomic impact assessment. The main role here is to develop these models and have a better way of evaluate behavior and mode shift effects, and assess, of course, the socioeconomic impact of these urban mobility interventions. The integration with simulations happen through the demand models, generating future travel demand and mode shift scenarios. Then the outputs of this, so the new OD matrix, are integrated into the Aimson simulation environment. And here is also important to highlight that we are doing these OD separators per gender and age. So you'll be able to analyze the impact of the travel shift also through the social perspective. And then we simulate traffic conditions the simulated traffic conditions are subsequently used to estimate safety, mobility, and economic impacts. The key contributions of all of this work is the cost-benefit analysis, the cost-effective analysis, the estimation of safety, health benefits, travel time, and environmental impact, and the network-level extrapolations of these interventions. Then from the human behavior modeling and safety-oriented simulation, again, here the idea is to develop the predicted human behavior models. We aim to analyze the behavioral response for infrastructure and policy change, and modeling vulnerable road users in the interactions and non-compliant behavior. This was quite a big innovation and a big win of the project, because also one of the challenges that we have when we start the PHOEBE project was the lack of information that we could find regarding non-compliant behaviors for VR use. So there's a bunch of sources, especially in the big data world, for vehicle interactions, but for pedestrians and cyclists, it's still very, very few information that you can get for those types of sources. Then the integration with simulations, we embedded the behavioral models into Aimson simulations. So basically we have probabilities of behaviors now, and making the simulations much more aligned with the real interactions between users in the real life. And the behavior outputs then influence the traffic dynamics, conflict, and safety outcomes. The output of this is also enhancing the risk assessment models with new calibration factors to estimate fatal and severe injuries. So key contributions of this work is the speeding, red light, and crossing outside designated area behavior modeling, and the transferability assessment across the cities. And the data needed for all this analysis, video analytics, telematics, survey data, and traffic observations. But we're going to hit a little bit more on some examples of the behavior modeling later on. And then for the dynamic safety assessments, in Aimson, the big thing is the simulation of future mobility scenarios. So it's still a very important tool for cities to understand the impact of interventions. So we'll be able to estimate the traffic flows, the speeds, and the interactions among users inside of the simulation software, and evaluate of infrastructure and policy interventions. In the integration with the simulations, then we have the star rating scores and the fatality and severe injuries estimations that by the end of the PHOEBE project are completely integrated as part of the Aimson Next software. So it will be someone that are doing scenarios evaluations aside of the simulation tools can see exactly how the scenarios evaluation impact risk on roads inside of the simulation tools. And then for the risk assessment, we're basically, as part of this project, we enhance the star rating models, and IRAP launched later on the version 3.10 of the pedestrians and cyclists model that was developed as part of the PHOEBE project. One of the big things as well that you will see a little later in the results, that we'll be able to provide dynamic risk estimation. So it means that we can see how the risk change through different hours of the day. And this can support some more dynamic response of cities to reduce risk for vulnerable road users. And of course, this can be used for network-wide safe performance analysis and to prioritization of high-risk locations and interventions. I think the key contributions I already mentioned. So there is direct integration between AIMS Next and the IRAP Vida that you hear a little bit more later on as well. This process is now running through an API, so it doesn't. The data exchange and the data fetching between the two softwares are much more automated. And and we can better do evaluations of interventions before implementation. So with no further ado, I'll hand it to Stella from N2A to guide you through the PHOEBE pilot results.
Great, thank you so much. Sana, are you going to be the one presenting? Because doesn't
up to you. If you prefer, I can present, or you can share your screen if you like.
It doesn't allow me, so yes, we can go with the from you. Okay, hello everyone. My name is Stella Rusu. I'm a research associate and PhD candidate at the National Technical University of Athens. And today I'm going to present the three pilot use cases that were implemented in the PHOEBE project. So coming to the city of Athens, can you please move to the upcoming slides? To the next one. Great, thank you. So the focus of the Athens pilot was the pedestrian road safety. We wanted to emphasize for the VRU KPIs. So we measured the speed, the modal share of pedestrians, the cyclists, and similar modes such as scooters. And the scenarios were created for different times of the day, such as the peak and the off-peak hours. And then coming to, the next slide, the three major interventions that were conducted in the city of Athens. So the first one was setting the 30-kilometer speed limit across the whole network. And the second one was the establishment of the bicycle routes. And the third one was the promotion of public transport, which was very crucial for the city of Athens, these three major interventions. Coming next to the simulation model, so we conducted a before and after analysis by incorporating to the simulation, to the AIMS simulation model, some naturalistic observed data. The data were acquired from the Athens Traffic Management Center, and we had accounts for before and after. So from the simulation models, the outputs in the beginning was that we had an increase of trips for the passenger cars and for the motorbikes, but a reduction for the taxis. Then we had an increase in traffic flow density and unfortunately travel time and delay. And we conducted some spatial analysis by road type and control type with having primary and residential roads having a flow increase and the secondary roads having an increase of crash risk. From the key preliminary results for the before interventions, we had an excellent fit for between the observed and simulated volumes with an R square above 0.9, which was very important. Next slide. And for the after interventions, we also had at our model a very strong accuracy, but the challenge is that we understood that we had to manage increased flow without compromising safety, and the slightly increased crash risk despite the improved multimodal efficiency. We conducted in the Athens pilot use case some stakeholder meetings so we can have feedback from the stakeholders. The results, coming to the next slide, were very important for our analysis and our results. So all of from the feedback from the stakeholder, we understood that the final KPIs had to be aligned with the policy framework. And coming to the next one, we had some strong emphasis from the stakeholders on the dynamic assessment of the interventions using the crash risk and the time to collision indicators. And from all the stakeholders, we had a very positive reaction to the use of AI and telematics, and there were clear concerns about the transparency and accuracy. Following to that, the stakeholders recommended that we had to strengthen the indicators that they were relevant, related to the VRU infrastructure, and all of the results, as previously mentioned, and the KPIs should be integrated in the sustainable urban mobility policies. From some surveys, coming to the next one, from the stakeholders, we understood that it was very important for them the recording of illegal behavior that needs to be linked to the transport policy making. And so coming to the next pilot use case for the Valencia city. Valencia city is very important regarding the touristic, as a touristic destination, as a tourist destination. And it has pedestrian and bike-friendly features as a city. And for the Valencia pilot, we had to assess and improve the cycling safety through the cycler app and the IRAP methodology, and of course implement the user behavior analysis and some simulations. The interventions now coming to the Valencia use case were focused on 4 cycling corridors that had a proximity to the University of Polytechnic of Valencia campus and tourist hotspots, and of course the presence of tram crossings. So the Valencia use case had some future scenarios that will be assessed and included the update of the bicycle facility network and the speed management, and as well as a consequence of the steep uptake in the e-micromobility usage. For the city of the Valencia use case, we had to analyze the user behavior in the situations of speeding and the non-compliance of micromobility users at traffic lights. So the simulation parameters were 4 revised intervention scenarios, calibrated simulations aligned with the previous work we implemented in the PHOEBE project, and the simulations executed for 14 hours per day with 4 applications per scenario. And now coming to the tested interventions, they were total in 4 as a number. So at the first one intervention, we had moving bike lane from sidewalks to roadway with physical separation. And to the next intervention, we had to establish a variable speed limit that downgraded motor lanes and adjusted to bike paths to 30 kilometers per hour. Coming to the other 2 interventions, the third one was to model a 30% increase in micromobility, evaluating the impact of a private versus a public shared scooter systems. And the fourth one was to reconfigure the road space by implementing a new parking lane next to the central divider. As for the Valencia local stakeholders, they also implemented 2 reflection meetings with the stakeholders. And what was very fruitful from their discussions was that the Valencia use case results, the IRAP most precisely in the cycler app results, were in line with expectations. And there was a positive reaction to the improvements of the AI-based image recognition in infrastructure assessment. And of course, a discussion on how the PHOEBE framework can fit within the existing Valencia traffic management system. And now coming to the last use case for the West Midlands. This use case focused on the behavioral change and the cycling road safety. So we had two aims and model simulations that they covered an area within the West Midlands. The first one covered 50 square kilometers from the Birmingham city centre to Solihull, and the second one covered 5 kilometers square to the south of Birmingham city centre. The interventions were now reduced speed limits from 40 miles per hour to 30 miles per hour, and of course the implication of mode shift induced for a new cycle infrastructure. And now to the next slide, we can see the area that was simulated, the one that it was in the Birmingham and the more generic area of the West Midlands. And so coming to the definitions of the West Midland use case, there were extensive simulations were used to forecast changes in traffic behavior and road risk. There was an assessment of the safety of cycling infrastructure using the lane patrol. We used some surveys to understand the public opinions regarding speed limit, which was very important for the stakeholders, and of course to predict the changes in mode shift towards an active travel and public transport. So the Birmingham area had 27 roads that had an operation of 40 miles per hour, but then it was reduced to 3 roads. So the question was, what will be the holistic impact of the 40 miles per hour to the 30 miles per hour speed limit change? Coming to the IRAP results, the IRAP model predicted a reduction in the speed limit from 40 miles per hour to 30 miles per hour will result in a 36% reduction in the FSI. And there were very big improvements to the safety of cyclists and pedestrians. So from the next results, we can see that there was an increase to the walking trips, to the walking total number of trips, and also a slight increase to the number of cycling trips, and a small reduction to the car total trips, which was very important for the West Midland use case. Now, understanding what can we establish by the safety impact of the new cycle infrastructure. Coming to the cycle wrap results to the next slide, we can see that for the before results had 20, there were 20 number severe injuries, but coming to the after ones, we had very big reductions to 6.91 severe injuries, and likewise for the fatalities. For the West Midlands, we also implemented some stakeholder meetings. There were 3 in total. And from all over the discussions that were conducted, we understood that the IRAP surveys were largely in line with the expectations, that the stakeholders mentioned that it was very important to have some pedestrian and some income from the local context, and highlighted some location where the FSIs was unaccountably high. So they discussed how to plan the insights from the PHOEBE that can be distributed to the relevant teams within the local stakeholders. So overall, several local authorities were in attendance to all the stakeholders reflection workshops through all the use cases, and of course the local authorities acknowledged the benefits and highlighted the great difficulty faced by the transport planners, and particularly when those changes inhibit or restrict the movement of the motorized vehicles. Thank you for your attention.
So now we go to Arnava.
Yeah, so I will in my desktop. Oh, thank you. Can you hear me? I mean, am I audible?
Yes, we can hear and
Okay.
we can see the presentation.
Okay. So thank you, Stella. Thank you, Shana. And thank you, Andrea. I will carry on with the modeling part. That is the demand modeling part and its integration into the project PHOEBE framework. So, as we all know by now, we have 3 use cases, Athens, Valencia, and West Midlands, and we have carried out all these modeling stuff like demand modeling as well as induced demand modeling for all these 3 use cases. So basically, we will first talk a bit about the motivation, then the actual demand modeling process, then the integration of the models into the big framework that we have already seen, then a bit of the results from the use case of Athens. So as we all know by now, the project PHOEBE, it acts as a integration framework for 5 different models or 5 different modeling components. So the first one is demand modeling, followed by behavioral, traffic simulation, road safety assessment modeling, and socioeconomic analysis. Of course, socioeconomic analysis is not a modeling component, but still, I mean, it is a separate component that can be identified as a modeling component. So here you can see on the right how these things are integrated with each other, and this is quite a big, big view of the overall framework. So as we have already seen the overall framework, and here I present it once again just to put into perspective where our demand models belong to. So as you can see, there are 2 basic steps. The first one is baseline, and the second one is the scenario setup step. So here stands the demand model, as you can see on the left in the baseline. So it takes inputs from risk safety assessment, and then model stops and then passes it on to the traffic microsimulation. Further, in the second step, in the scenario setup step, the interventions are set up in traffic microsimulation as well as the road safety assessment model, and then the demand model takes the updated values and then run the modeling steps and pass it on to the other components for updated KPI. So basically, in baseline scenario, we get the outputs which are like baseline KPIs, and for the scenario setup step and the scenario evaluation step, after running these steps, we get the updated KPIs for each and every intervention. So the first question, what is the definition of demand modeling in this particular case of PHOEBE, or to be put into simpler words, why we are calling it demand modeling? So in a classical 4-step macroscopic simulation theory, we have 4 steps: trip generation, trip distribution, mode choice, and then route choice. So in this particular project, we are dealing with the third as well as the first. So in the first, we have trip generation, but in this particular project, we deal with induced demand, which is a kind of trip generation step. So that is the first step, trip generation, and then we have the demand modeling. The second part is the mode choice. So when we integrate these 2, we call it demand modeling in this particular context. So all in all, we have 2 separate models, mode choice models, as well as induced demand models, which are abbreviated as ID and MC for mode choice. So the next question arises: why demand modeling matters in PHOEBE? So as far as we know by now, all the safety things that are happening on road, the safety issues, they are more or less depicted by the microscopic simulation models. But is it so? Is it always so that we can depict each and every thing that's happening in road safety by traffic microscopic simulation? The answer is no, because the road safety outputs also depends on stuff which happens at the macroscopic level. Say, for example, if a person inherently chooses a mode that is more riskier, then probably the safety outcomes will differ. So this is the reason why we need mode choice model, which is inherently a macroscopic simulation stuff in our framework to reflect the overall macroscopic stuff into our outputs of this particular project. So in PHOEBE, we answer the 3 questions through demand modeling. So the first question is, who changes the behavior? That is mode choice and induced demand. So which are the different person groups, age group, etc., and why they change. Say for example, due to the change of travel time, cost, associated risks, etc. So this is our first question. The second question is, once the people change their behavior, what shifts into the network due to the change in macroscopic behavior? That is, when people switch to another mode, traffic conditions and exposures, they also change. So this a safety intervention can actually reshape both the demands as well as traffic patterns and therefore the exposure. So we actually answer these 2 questions. So this is where the integration of demand model takes place. And finally, the answer of these 2 questions feed the third question, that what does that mean for appraisal? And that is the third part, which is the socioeconomic analysis part. So having said that, since we had some extra metrics in our mode choice model, like risks and stuff like that, so we had to fill 3 separate surveys through panel company in these 3 use cases. So here what you can see is the results from the Valencia survey. So in each and every survey, we had 500 responders. They actually responded 8 state preference scenario for mode choice modeling, as well as 4 for the induced demand modeling. And here you can see the quota outputs and survey time completion as well. So having said that, in demand modeling, we actually estimated the models, then we calibrated the models, and then we tested the models. So it was not out of, it was really a common practice that what we followed in this particular project. We used our survey inputs to estimate the models, and we used R as well as Apollo package in order to estimate the models. And these are like parsimonious multinomial logic models. Then we actually calibrated the model using 2024 data, which actually fixed the model to the baseline 2024. And here you can see the explanatory variables for the mode choice, which were like travel cost, in-vehicle times, weight egress time, then travel distance, and associated risks relative to the reference mode, which was public transport. Since public transport came out to be the safest among all the other modes in all these use cases. Then in our induced demand model, were estimated to forecast or calculate the extra trips due to the changes in these explanatory variables. And these induced demand models were only developed for the shared micromobility. So we, as explanatory variables, we have delta travel time, or the difference of the travel time in vehicle time, travel cost, and other stuff as well that you can see over here. And then these are the mode set for mode choices. So we had car in all use cases, public transport in all use cases, motorcycle in the case of Athens, and then shared micromobility for all use cases, private micromobility for Valencia and West Midlands, and walk for all use cases. And as I have already explained, that the induced demand model were only developed for the mode of shared micromobility for all the use cases. So the models, as I have already described, we segmented the models according to the age and the gender of the particular use case. And then we used year 2024 data to calibrate and validate the baseline model. So now talking a bit about the integration. So the question is how these two models actually integrate with the big framework that we have already seen. So the mode choice models integrates typically with two other modeling components that are traffic microsimulation model through OD matrices interface, and then road safety assessment model through the associated risk metrics or numbers, which are used as explanatory variables in our mode choice as well as induced demand model. So here you can see a simple flowchart of the whole integration process. So we have the mode choice models here, and we take the inputs from the road safety assessment model as well as the traffic microsimulation model. Then we run the model and we generate the segmented matrices, OD matrices. And then we feed these segmented OD matrices for the baseline into traffic microsimulation, where the interventions are again turned on, and then the whole loop goes on, and then we have the new segmented OD matrices on which we run this induced demand model with the help of the difference in the explanatory variables, and we get the extra trips that we add in the segmented OD matrices and then return it back to the traffic microsimulation. So it is not a very straightforward method. There are quite a few loops that you can imagine in this particular case. So here you can see the big picture of the integration. So on left and on right, you can see the modeling steps stacked together. And then in the center, you can see how these modeling steps actually integrate with risk assessment model as well as traffic microsimulation model. So having said that, since we are integrating these models, so we have to have very strong integration protocol. So here what you can see, this is the integration protocol of all the modeling components that we have. So each color depicts one model type, one model component, and these cells that are marked with P and D, so these are basically the data exchanges between these different models in order to integrate these models together in the framework. So having said that, we also had to face a few challenges while integrating the stuff, because we were dealing with macroscopic models and microscopic models together, and we needed to integrate them. So this was a big issue, which because mode choice as well as induced demand, these are macroscopic model, and traffic microsimulation is a microscopic model. Then we had to see through how we can integrate and preserve the consistency. On top of that, we also had a few consistency issues like scenario definition, zoning, mode labels, etc., that we had to solve during this integration. Further, we also had some data requirements as well as interoperability between these models that we had to take care of in order to make this framework functional. So having said that, here you can see the results from the Athens modal shift in terms of number of trips. So here, the alluvial plot that you can see, this is the number of trips, the modal shift. In the left, we have the baseline, and on the right, we have the scenario 1. For the second one is the baseline and scenario 2. Here you can see the modal shift in terms of trip kilometers. Similarly, what you can see here is the scenario-wise trip length of all the modes in Athens. Now, the thing is that there may be a question why there is very small changes in the trip lengths. The answer is we were only modeling very small areas of these particular use cases. So there are changes, but these changes are not substantial. In order to have substantial changes, we have to model really big areas where trip lengths are longer. Then it will be really particularly visible. So, since we have mode shift models or mode choice models, we can also use them for some secondary analysis. So, one analysis that you can see over here is the emission calculation from the output of the mode choice model and the induced demand model. Since we have the trip kilometers, these numbers can be easily used to calculate the scenarios for emission scenarios for any use case. So here you can see how all these pollutants are changing scenario wise. Okay, so we have the baseline, which is this straight line at 0, and then a box and a cross, which denotes the different scenarios. So having said that, thank you from my side. This was all about demand modeling. Thank you.
I don't know. There is a question for you. I don't know if you want to reply right now, very quickly, or if you prefer to reply by writing.
I will write and reply.
Okay, perfect. Thank you. So we can go to Amir now.
Yes, thank you. Let me just quickly share my screen. Perfect. Yeah, so good morning, everyone. Amir here, Assistant Professor of Transport Safety at TU Delft. TU Delft led the behavioral modeling component of PHOEBE, and so I'm going to walk you through just very briefly the general motivation and the methodology that we developed, and at the end, some of the results that we got. So starting with the motivation, the main motivation behind the behavioral modeling was that we reviewed the state of the art, and we noticed that the two main elements or components of PHOEBE, so road safety assessment and traffic microsimulation, basically they lacked human behaviors. So we noticed that road safety assessment primarily focuses on infrastructure, traffic conditions, and road environment to be able to produce star rating scores. Also, traffic microsimulation tools, the existing ones, they mostly aim at traffic modeling and demand modeling. However, they are also a little bit used to derive and extract surrogate safety measures, but yet they are still mostly focused on kinematics. At the same time, we know from the literature that about 95% of crashes are primarily caused by driver behavior or behavioral factors. And so we noticed that there's a gap in that human behaviors are not explicitly represented in traffic microsimulation and road safety assessment. And I wanted to just add a very quick but very important remark here. We are aware that human behavior is a broad term. It can basically indicate many different elements of the behavioral aspects of humans. However, there is a niche focus within the scope of this project, and the focus is really on the non-compliance behaviors, kind of a human factors type of behaviors in PHOEBE. And so the aim and the objective was indeed to add behavioral factors, or these non-compliant behaviors, into traffic microsimulation and road safety assessment, and finally to adjust the road safety assessment with these non-compliant behaviors. To do so, we developed a methodology which basically consisted of three main elements, starting with understanding road users' behavior, or these non-compliant behaviors, and then integrated them into traffic microsimulation, and then scaling it up into more macroscopic road safety assessment. And so I wanted to go back to the flowchart, the framework that was shown to you in the beginning. And here is where we are. So the behavioral models have interactions with the traffic microsimulation and road safety assessment. And again, the idea was indeed to learn from real world traffic interactions, to integrate them and to test different kind of scenarios and interventions in microsimulation, and then to scale it up to road safety assessment. Again, I want to also present a very simplified version of the process of this methodology. So we started by learning human behaviors from real world data. I'm going to walk you through the data in a second. But then we first started by developing some discrete choice models of certain behaviors. The discrete choice models would provide us with probabilities of the behaviors. And then we integrated those probabilities into traffic microsimulation. Then out of traffic microsimulation, we extracted the total number of conflicts using surrogate safety measures with the behaviors applied. And then we would apply the behavioral models, different types of behavioral models, well, specifically extreme value theory models, to develop a relationship between traffic conflicts and crashes. And out of that, we applied, or we developed FSI calibration factors, and then we gave those factors to road safety assessment to basically adjust the methodologies of road safety assessment with the behaviors. Now, starting with the first phase of the methodology, indeed, we wanted to, again, learn from the instances of specific road user behaviors. We also integrated many different other types of inputs, including road geometry, traffic composition, also individual characteristics, demographics, past behaviors, psychosocial attributes of people, and out of all of those factors, we developed discrete choice models for certain behaviors, which is basically providing us the probability of the behavior as a function of all of those inputs. Then out of the discrete choice models, we get the individual behavioral probabilities. However, again, based on the probability theories, these individual probabilities can also be translated into proportions. So for example, a 5% probability of going over the speed limit basically would mean that out of 100 vehicles passing through a section, 5 of them would go over the speed limit. So we kind of translated these individual probabilities into the proportions of the behaviors, and then we input that or integrate that into traffic microsimulation, and then we run the simulations at the end of this phase. So 2 of the behaviors, so speeding, going over the speed limit, was one of the specific behaviors that we tested on. We integrated that behavior through the Aims on Next API by modifying the speed acceptance parameter of the microsimulation. Also, again, because we had a lot of inputs from network characteristics, so roadway geometry and roadway conditions, the network transitions. So when there is a transition from a part of the network to another part of the network, triggered basically activation or deactivation of the speeding behavior. And the behavior is activated based on the behavioral probability and a random draw. So basically, we gave a probability out of the discrete choice models to traffic microsimulation. Traffic microsimulation generated a random draw. If the probability was less than the probability that we would give the traffic microsimulation, then the behavior, the speeding behavior, were basically operated, otherwise not. And so here's a screenshot of the microsimulation. And I believe, if I'm not wrong, I believe the red dots are basically the places that there is a speeding behavior in the network. The other behavior that we tested on was the pedestrian red light violation. So when there is a red light for pedestrians and pedestrians run the red light. Again, we implemented that in the Aims on Next for Athens use case only. the violation was assessed only when the pedestrian signal was not green, so it was red. The behavior was activated when the calculated probability exceeded the threshold. And the threshold, we chose the 50% as a threshold. So if the probability was more than 50%, then the pedestrian were allowed to basically cross the road even when it was red. Now in the second phase, after the behavior is integrated into traffic microsimulation, then now we have to basically scale it up into macroscopic road safety assessment. The problem or the challenge was that the output of traffic microsimulation is microscopic, as the name implies. So AIMSON or traffic microsimulation would provide us with conflicts, whereas IRAP, so the road safety assessment, is basically based on crashes. So all the crash modification factors and the star rating scores are based on crashes. However, from the output of traffic microsimulation, we have conflicts. So we had to basically create a link between conflicts and crashes. And to address this challenge, this is the methodology that we developed. I'm just going to walk you through very quickly on the overall methodology. Basically, we run the simulations with the behavioral equations, discrete choice models. We extracted the conflicts by the behavior. On the bottom side, we also run the simulations without behavioral equations. And so we extracted conflicts without the behaviors. So on the one hand, we have the conflicts with the behaviors. On the other hand, we have the conflicts without the behaviors. And in parallel, using actual data, video data, we developed crash conflict relationships using extreme value theory models. And then in parallel, at the end, we would have an empirical relationship between conflicts and crashes. And so feeding the conflicts both from with the behaviors and without the behaviors into this relationship, then we would get out of that the crashes, basically, or the number of crashes with behaviors and the number of crashes without behaviors. And we took this ratio of the two types of crashes with and without behaviors, and we developed a modification factor for road safety assessment. So this is the way that we scale it up from microscopic to macroscopic road safety assessment. In terms of the implementation, again, we had 3 use cases. We applied or implemented the speeding behavior, so going over the speed limit for car drivers in all the 3 use cases. In the Athens use case, we had also non-compliant behaviors of pedestrians, so red light violation of pedestrians. And in the Valencia use case, we had non-compliant behaviors of micromobility, so red light running of cyclists and e-scooters, basically, in the Valencia use case. Due to the lack of time, I want to only focus on the results for the Athens use case. So in Athens, this is the equation, the probability equation, or the discrete choice model, estimate discrete choice model for the red light running behaviors. So you see we get the probability of red light running by pedestrians in this equation, which depends on the traffic being high or low, the crossing width of the road, with being in a rush or not, the age of the pedestrian, and the past behaviors of the pedestrian. So whether the pedestrians did a red light running violation before, whether they were in a hurry and they were not looking, and so on. And so these are just a few factors out of a long list of factors that we tested in, and these are the only few factors that were statistically significant for the sample in Athens. This is also another one, which is the probability of crossing outside of the designated area, kind of a jaywalking in Athens, again, depending on an array of factors coming from traffic characteristics, roadway geometry, but also individual attributes of pedestrians. And finally, these are the results after integration. So you see, these are the percentage change from when the behavioral API is off to when the behavioral API is on in the traffic microsimulation. And you see that when the behaviors are integrated, the median of the minimum TTC was increased by about 9%. and many other indicators also increased by significant or substantial percentages, which basically shows that when the actual human behaviors are applied or implemented, then there is basically more risky behaviors or risky outcomes in traffic microsimulation. And finally, these are the results of the road safety assessment. So integration of human behaviors into road safety assessment. And you see that after integrating human behaviors into road safety assessment, there are indeed places or network locations that there is a significant difference between the FSIs after integrating the human behavior. So the FSIs after integrating human behaviors have increased statistically significantly after integrating human behaviors. So this was a very brief overview of the behavioral component in PHOEBE. I'm happy to answer any questions either now or after in the Q&A part. Thank you.
Thanks a lot, Amit. And if there's no questions right now, we can go to Antonio from ANSA.
Yes. Okay, I'm just sharing the screen. Right, so I hope you can see my presentation in presentation mode. So good morning, everyone. Thank you. My name is Antonio Pellicer. I'm a senior scientific researcher at Aimson. And today I'm going to be presenting how we have brought two different, let's say, worlds. On one hand, we have the traffic simulation, and then on the other side, we have the safety assessments via the risk ratings. But before we start, let me introduce the two pieces of software or platforms that we have used in this sense. On one hand, we have the Aimson Next traffic simulation software, which is a multi-resolution, multimodal simulation platform in which we are able to simulate movements of vehicles, pedestrians at different levels of detail. So we can easily obtain congestion levels, speeds, flows on different areas of the network. However, these models, these softwares are traditionally, let's say, safe by default and have been operated in isolation from safety frameworks. Then on the other side, we have the IRAP-VIDA. So this is the, let's say, the IRAP's platform for road safety data management and risk assessment. The VIDA actually delivers this, what is called internationally recognized star ratings, and is used by governments worldwide. So basically it rates the different road sections into 1 to 5 stars, being 1 star the highest risk and 5 stars the lowest risk. However, the limitation is that VIDA actually relies on manually, let's say, entered static inputs from road infrastructure, which are basically quite disconnected from real life, let's say, operational inputs. So in this project, we aim to incorporate the operational outputs from the simulation into the safety assessments and vice versa. So in this sense, we have two best-in-class tools. In this case, Aimson Next and IRAP-VIDA, but working in silos. So the integration of these two components closes the gap. So now practitioners can evaluate mobility and safety together in a single iterative workflow. And talking about workflows, this is what we have proposed in the project. Basically, it consists on 3 main steps. The first one involves the network compatibility issues. So we need to make sure that there is a spatial association of network IDs between both networks. So the road sections in Aimson Next need to have an associated road section in the VIDA platform. Then the second step involves the data harmonization. So we need to create a process that converts the data into the different formats. So this can be read by the different platforms. And finally, we have the data flow routine, which basically this is responsible for exchanging the information between the different platforms. In this presentation, for the sake of time, I will not cover the network compatibility issues, and instead we will focus on how this is harmonized and how this is this information is exchanged between between both platforms. So the key idea here is to have an integration layer for, let's say, bidirectional data exchange. And this is basically done in two phases. On phase one, let's say traffic simulation results, such as, for example, can be volumes, speed, vehicle compositions, are sent to the safety assessment platform for the recalculations of the star ratings based on operational, let's say, variables from the simulation side. And then the second phase, phase two, basically once these updated star ratings, considering the operational parameters, are recalculated, then these values, these star ratings, are sent back to the simulator in order to be visualized within the user interface using the simulation software. Now, this diagram shows the integration architecture with a little bit more of detail. So basically, phase one, as we mentioned, goes from Aimson to IDA-BIDA. In this case, as we mentioned, we are extracting the information, the outputs from the simulation. Then we build what we call the CSV filing with all the information from the simulation, as well as the information, the existing information from the IDA-BIDA infrastructure data. Once we have both files combined, then we upload this new information into the BIDA platform so they can recalculate the new star ratings. On phase two, once these recalculated star ratings are done, then we just need to download this information and then import this information into the simulation in order to and also to create, let's say, the view modes in order to visualize this information within the user interface. Now, in the following slides, we will go step by step in the integration process, but at the same time, we will apply each step to a case study, in this case, in the Birmingham case study in the West Midlands, within the PHOEBE project. So, going into the phase one. So as we said, the first step is to run the simulation and then extract the different tables containing different operational variables, such as traffic volumes and speeds. Then once we have this information, so all the results, we then need to download the existing information from the infrastructure data from IDAP. And we need to merge both data sets in order to have like a complete CSV file with all the information. So this can be sent to the BIDA platform. Within this CSV file, as I mentioned, we are combining both things. So first of all, as I mentioned, we are having the existing data from the infrastructure. So we can contain, for example, road geometry, different intersection types, different road conditions that normally in a simulation is not part of it. And these values are not overwritten. These are per se the values that we take from IDAP. And then we are adding the operational parameters, such as the speed limits, vehicle flow, which is converted to the annual average daily traffic, and different vehicle composition. So these values, together with the existing values, we are creating this complete CSV file. And finally, this information is sent to the BIDA using the BIDA API. And then once BIDA receives all the updated information, they recalculate and update the star ratings based on the operational parameters from the simulation. Now we move to the second phase, in which once we have recalculated all the star ratings, then we transfer this information to the simulation with the view modes. So the first thing we do is to download the updated information. So we will obtain tables such as this one. So in each column we will get a star rating per vehicle, per road user type. And we need to make sure also to have the different IDs, as I mentioned at the beginning with the network compatibility issues. So we need to make sure that each road section in Aimson has an associated ID within the beta platform, so this can be assigned to the different road sections. Once we have this done, then we need to import this information to the Aimson Next software, which in this case, we have done it by adding different columns into the different road sections, so we can add this information. And finally, we can build the different view modes, so we can visualize this information in the user interface. So just to conclude, to finalize this presentation, as I mentioned, this is a bidirectional automated data change on phase 2 and phase 1 and phase 2. Then we are using the IRAP data, and we are just updating 7, let's say, variables. We are not overwritten the rest of the IRAP infrastructure data. Of course, this pipeline can be run for any simulation scenario. The only condition, of course, is to have this network compatibility issues between both networks. We have identified also some limitations, which basically we need to enhance the full automation of this process, because at the moment both phases are automated, but the calculation of the start ratings needs to be enhanced for the automation of the full process. And within the future world, we also would like to have kind of live operational systems. So in order to get simulation data, we will get real-time data, so we can improve and enhance this as a live operational system, and then transfer that to the simulation in order to have more like a digital twin with the safety parameters also included within this operational system. And that's all. Thank you. I'm happy to answer any question in the chat or right now. Thanks.
Thanks a lot, Antonio. And yeah, for the ones with us, don't be shy about asking questions or writing in the chat. And to finalize, we go back to Shanna with more details on the results.
Great. Thank you. Thank you very much. Thank you for all the colleagues also that present more on the PHOEBE development enhancements. I have the task then to unpack a little bit the results of a 3 years project. So there's a lot of things to mention. Bear with me for an additional 10 minutes, and then we open again for some questions. So for results here, we are talking about like 2 key groups. One that I'm calling like technical results, but it's more like on the project results, the things that the project can offer. And the other type of results is the policing side. So what are the learnings from the use cases, and that are with the application on all of this work in use case, real use case scenarios? And how is the learnings from this that I will be presented through the PHOEBE framework key performance indicators? So in terms of the technical results, the main one for us is the framework. I know that you saw the framework with the different structures later on, but I want to present this one here just to show you how we really operationalize all of this that you just heard from my colleagues today. So after we developed the methodological framework, we had to put it into operation. So put it into operation means to establish like this timeline, establishing the data flows, which are the external data sources, but which are also the internal data sources, how one model can really feed into the other, to the subsequent tasks. So we basically have all of this documented now with this, again, 4 main components of risk assessment, traffic simulation, mode shifting, those demand models, and human behavior. And this integrated into these 3 stages, that is the setup stage, the simulation stage, and the refinement stage. If this seems a lot, and also replying a little bit from the question that was in the Q&A, there is also this possibility of using the PHOEBE framework in a type of modular approach. So ideally, of course, it will be nice to integrate all of the 4 components, because then you can really see the holistic impact of the interventions in terms of safety that we want to have at the end. But if data is not available, if the cities don't have proper the knowledge or the right people to conduct some particular parts of the framework, you can always plug one of these components into traffic simulation, one or more, that already some enhancements will be possible. So we are looking at this from a perspective that currently cities are only looking for a small piece of the pie. So we want to add some additional things to really provide a good trade-off between safety and the other operational, environmental, or social indicators that they could be assessing when testing interventions. So please bear in mind that although this might seem complex from what we are presenting, you can always take a more simpler approach that already some benefits will derive from this modular approach. So the other outputs or results that we have in terms of what the project brought to the bigger audience is the Star Ratings new model version. So if you follow IREP, you might have seen that we just launched the version 3.10. With the version 3.10, we have enhancements on risk assessment for pedestrians and bicyclists, more specifically, including new crash types for cyclists, and also updates on the risk factors based on evidence and research that we conduct as part of the PHOEBE project. So we have now better infrastructure risk prediction for these vulnerable road users, and now this is globally launched for all IREP stakeholders, and the V3.10 is now the new standard version of the model that any IREP assessments should follow. You just heard Antonio talking a little bit about the AIM2 safety model. So you saw in details how the Star Ratings now are integrated into the AIM2 Next. This is already available for those of you that want to do this type of analysis, but there is also the development of the APIs that incorporate the human behavior model and the mode shift in induced demand outputs inside of the traffic simulation. So now we have a much more powerful software in terms of assessing these behaviors, these human and travel behaviors in cities. Oops. I mentioned at the beginning that we want PHOEBE to be a type of like blueprint of how this assessment should be done. We have this blueprint now. So in deliverable 5.2 that it's available in the PHOEBE website, we have what we call the framework protocols. And in the framework protocols, we describe in a lot of details how the framework operates, which are the necessary developments for each component, how the integration happen, which are the data flows, how do you calculate the performance indicators. And we have one interesting piece of work here that we call the PHOEBE required skills and knowledge. So we have there listed everything that you need to know to replicate the PHOEBE framework. Here, of course, we are not, for example, teaching how to estimate mode choice modeling, but we are saying, okay, if you want to do this piece of the framework, you need to have someone that have the proper knowledge to estimate these models. In terms of PHOEBE publications, so we have a different type of publications that was produced as part of the project. Of course, there are the deliverables that present all of the technical work, and they are available in the PHOEBE website. There are also a lot of scientific knowledge produced, and they are already published or in process to be published. So here I just have like two examples of academic papers that were derived directly from the PHOEBE outputs. And also quite interesting gray literature that we have produced together with other projects that are focused on road safety. So PHOEBE is part of what we call the road safety cluster project. So there are projects that aim to enhance road safety from different perspectives that are part of this cluster. And we work together to produce this document that we call Advancing Road Safety Through Data, Challenge Solutions and Policy Insights from EU Road Safety Project. So we investigate through all of these projects. So we have 11 projects, if I'm not mistaken. What are the challenges they face in terms of data gaps, data standardization, harmonization, etc., and how they overcome this challenge? Which are the innovative solutions they put together to really produce very good results, bearing in mind that these gaps and challenges on data exist. So I really suggest that you have a look on that particular paper. In terms of technical developments as well, we have what we call the PHOEBE impact factor. So we're going to be launching this platform quite soon for the next days or weeks. So stay with us and connect with us through our social media and website that we're going to publicized when this is launched, that it's basically produce impact modification factors. So it means like for a city that wants to do an intervention similar to Valencia or similar to Athens, for example, they can come here and see for some particular locations, for example, bear in mind the number of lanes, if it's out of peak hour, if it's urban or rural roads, if I reduce the speed limit, which is the impact that I should get. So we are finalizing these calculations now that are the final product of the project, and we'll be launching an interactive dashboard where you can have a look on that. Another important thing is, I mentioned data gaps. So we here, as part of the PHOEBE project, are committed to put all the data produced as the project in an open source format. So we are doing this through the Zenodo platform. So if you go to Zenodo and search for PHOEBE project, you will be able to see there not only the deliverables, but as I said, all of the data that we are produced as part of the project available for anyone to download and play with the data and work yourselves. So of course, bear in mind, this is very focused on the use cases, but it's very interesting to see, again, some results for Athens, Valencia, and West Midlands available in the Zenodo website. In terms of the policy insights then, so this was like the PHOEBE, let's say, exploited results, the project results. Now we're going to look very quickly into a bit more tangible results for the use cases. I know Stella presented a little bit from Athens, Valencia, and West Midlands. I just want to here go briefly through some examples to really showcase what the project can produce, because I think one of the things that we were committed as well, it was on transfer all of this very technical knowledge that we put together in the framework to very easy to understand tangible performance indicators. So I'm just going to show you briefly some examples here of what the project produced. So going to Athens first, just for us to have like an overview of everything. Again, if you remember what Stella explained, the Great Walk project in Athens working to create more space for pedestrians and cyclists, including pedestrianization of one of their main streets. And there was another scenario that was with the speed limit reduction. But if we only look for the Great Walk intervention, this is basically what we can get as results. So in terms of the health and safety indicators, we see a 12% reduction in fatalities and severe injuries. And you will see that there was an increase on segments assessed above road safety targets. So the road safety target in here, we are talking about 3 stars or better. So in the baseline, we have 18% of the network with segments classified with at least 3 stars. With the interventions, we move this to 93%. So it's already a very impactful safety results. In terms of mode shift, there is 2% decrease in the motorized use. As Arunava also mentioned, these numbers are quite small because the network is very small. But we see overall high uptake, into non-motorized modes, especially for elderly people. In terms of environment, we see reductions in CO2 and NOx emissions. In operations, we see 70% reduction in travel time and 13% reduction in travel distance. There are more KPIs available. I just got some key ones in here, but for you to have a look of how broad we got in terms of information that cities can look to really evaluate the impact of this intervention. So the idea here is that it will be possible to do trade-offs between safety and operation, between environmental operation, between environment and safety, and etc. So one example of this is the speed limit reduction scenarios. So here we are looking for Athens and West Midlands. In case of Athens, again, it was a reduction of 50 kilometers per hour to 30 kilometers per hour in the main corridors. You see there is a big impact on fatality and severe injuries, 50% reductions, although we see an increase of drivers traveling beyond the speed limit in these scenarios. And if we look for, and there is also reduction in the risk for pedestrians and bicyclists. If we look for the operations, we see reduction in travel time, reduction in travel distance, but a small increase in the delay. So it means, okay, cities might accept that we're going to have an increase in delay because we're going to have a very big impact on safety. Same for West Midlands, 47% reduction in fatalities and severe injuries, 35% reduction in the risk of pedestrian, 14% for bicycles. We go from 1% to 25% of drivers traveling beyond speed limit. And here the reduction is from 40 miles per hour to 30 miles per hour. So we see a bigger impact in the operation. So 20% increase in travel time, 2% increase in delay, although there was a reduction in travel distance. But again, if cities are only looking for the simulation results and only the operation impacts, they are really missing the big benefits of safety in this type of intervention. So no one will do speed limit reduction, for example, if only looking for the operational parameters, because we might know that we're going to have some impact, but we need to see that, okay, for the safety perspective, we have a very big gains in here. So it's the idea of having all of this information to really work on this trade-off. And for the cities, be aware that, okay, if I have increasing travel time, I might need to test then additional interventions and piling in interventions to really see how can I minimize the operational impacts, but also always trying to maximize the safety benefits. For the one example of the implementing bicycle facilities in West Midlands, so Stella also showed you these examples. Of course, we understand that there's no such a thing as 0.2, 0.9 fatalities, but here was basically a pure mathematical example of how the models operate. Luckily, the corridor is small. There are a very small number of crashes in this location, although there are some very big impact on severe injuries. So with the dedicated segregated cycling facility, we can move to 20 severe injuries to around 7 severe injuries with the cycling facility implemented. And again, with a very big impact on the uptake of bicycles and share mobility. One final example is the intervention in Valencia, where, and this one was quite interesting one, because we are basically, with the other use cases, we are always looking for interventions that we were expecting to increase safety or reduce the risk. With this one specifically, we had no idea. So the city really want to implement like a parking lane together with the median. So we try to see what were the impact of these interventions in this corridor. And please be aware that this is a very important arterial street close to the Polytechnic University of Valencia. So as you can see now, there is like a three lane for vehicles with a parking lane with a very big blocks. So there is a high speed and high flow scenarios in this particular intervention. And here, with the different hours of simulations that we will be able to get, we also be able to see how the risk change over the hours. And this is quite an interesting thing for cities to move to even more innovative solutions, because then they could, for example, understand that if it's one of the hours I see the risk getting too high because the speed is getting high, then I can plan, for example, speed enforcement interventions only for those particular hours. Or I can see, let's see, for example, if for some particular hours the risk is too high for cyclists, I can create some type of like a dynamic allocation of space and creating segregated bicycle infrastructure only for those hours where the risk is high. The other ones I can have bicycles sharing the lanes, for example, with vehicles. Maybe not for this particular corridor, but this is something that the dynamic risk factors risk assessment can support. So here, as you can see, the first one is the baseline. So you see this is the star rating. So as close to 0 as higher the risk. So here you see the risk getting high only at the intersections for pedestrians. But with this new parking lane, we see then more people crossing outside of the designated area, so crossing in the mid-blocks. So the risk in the mid-block sections for pedestrians got high. And here it's even more risky because you see the cars parked, for example, so it's really hard for drivers to see the pedestrians that want to cross in the mid-block areas. So this is basically what these charts are showing. So just very briefly on the overall results, I think we have 3 use cases that can really inspire other cities on what to do to reduce safety. So in the case of Athens, the reclaiming of the public space and the reduction of the speed limits really exemplify how these regulatory measures can complement infrastructure change to reduce risk of vulnerable road users. In the case of Valencia, I just present this intervention, but there was other two very innovative interventions tested. For example, one that we test how the safety impact of reducing the speed limit of different lanes. So basically, the lanes more to the left is going to have smaller speed limits than more to the right is going to have smaller speed limits than the one to the left. So you can see the results of this testing scenarios also on the PHOEBE deliverables. And in the case of West Midlands as well, this idea of taking just the results of the testing of reducing speed limits in some key corridors, how can we really scale this up to the whole network of West Midlands? So we test that as part of PHOEBE. So please get in contact with our deliverables and materials that you'll be able to see more on PHOEBE results and policy insights. This is what I have for now. Thank you very much, and happy to take any questions and respond to any questions that you might have at this stage.
Thanks a lot, Shanna. I think we are running out of time, but there is one question about the material available to make replicability studies. I don't know if I can answer that.
Yes, I can take that. Yes, definitely. The PHOEBE framework protocols are developed with this objective. So as I said, they are part of deliverable 5.22. So you can find deliverable 5.2 in the PHOEBE website. And here we put a lot of effort on detail exactly which are the necessary stages to replicate all of these studies, including like the mode shift modeling, the behavior modeling, the risk assessments, but also the connections with the APIs inside of the AIM Next software. So please feel free to go to the website and check deliverable 5.2.
And just a final one on PsychoRep. If there was anything from PHOEBE that can be used to further develop the PsychoRep.
Yes, thank you for the question, Magnus. In fact, we test the fatal and severe injury estimations for PsychoRep in PHOEBE. So this is not publicly launched yet. So currently the PsychoRep only do the risk assessment and safety treatment recommendations. But until the PHOEBE project, we didn't have any testings or any models that were capable to do the fatal and severe injuries estimations based on the PsychoRep results. And this was developed as part of the PHOEBE project. So if you want to hear more from that, again, the PHOEBE deliverables, but feel free to get in touch with me that I can share some specific materials about this. So thank you very much for the question.
Perfect. So I just leave here again the website so everyone can check in more details, as Shanna said, the deliverables. There's also easier to get in touch with everyone, check all the partners, and just have your eyes there for our final deliverables. And with that, I think we can wrap it up and finish. So thanks a lot for the ones who stayed with us, and thanks for the colleagues for presenting all the work that we did in short presentations. So the recording of the webinar is going to be available also. And that's it. Thanks a lot for joining us.
Thank you, everyone.
Thank you.
Thank you.